All right, so last, I guess it was Wednesday, right? We talked about synthetic division. So we came up with another kind of easy way to do division of polynomials. Let's maybe practice one of those real quick.
You came up with that?
I did not come up with that. We looked at that. It's a pretty common thing. You use it when you can. It makes things easier. Let's do a quick example. Okay, so let's try this one. So what do I do here? Tanner, how do I set up synthetic division for this? What goes where? Okay, hey, attention up here, please. Where's the numerator go? Okay, but remember, for synthetic division, we don't have the division fraction. Right, so we got our... Okay, what goes out front? Okay, the 0 of the denominator, good. So we're going to take the 0 of the denominator is 3. Right, so if we set it equal to 0 and solve. Okay, and what goes top row of our bracket? Coefficients. Okay, so we got 1. And there's our remainder box, right? Okay, so then now we're gonna bring the 1 down. Whenever a number appears below the bracket, what do?
Multiply it by 3.
Multiply by the 0 up front. Good. So 1 times 3 is 3. Add it. Good. We add. We don't subtract. 8. Okay. Okay. And is that right? That's not right, is it?
You guys are tripping.
Yeah, that's not right.
Yeah, that's right. No, you guys are 27. Yeah, it's 87.
Oh, okay. All right. I guess we're good. Yeah, that's right. Never mind. So then we get 92. And so what is this equal to then?
X squared.
Okay, so there's going to be a squared there. There's an x there. And then less than 0. Right? Those are pretty bad. I got it. But we're just going to write it up here anyway. So we get this 1 becomes a 1x squared. This 8 becomes an 8x. And then that x to the 0, that 29 just becomes the constant, 29. Okay, and then where's the 92 go?
Above the x.
Okay, so that's what remains over the denominator, right? And then the denominator was just x minus 3. Okay, very simple. I gave you guys a couple ones that were just a little bit harder. What about something like this? What did we have to do when we ended up with the denominator being, the coefficient of x in the denominator not being 1? Okay, good. So we need the bottom to look like x plus or minus a number in order for synthetic division to work. So we're just going to divide both the top and the bottom by 2. Right? So we would just rewrite this essentially. I mean, we wouldn't have to rewrite the whole thing. We just know that out in front, the 0 of the denominator is going to be what? Negative 5 halves. Make that. Okay, but what's going to happen to all the coefficients then?
They get divided.
Got to divide by 2. Good. So we're going to get 1, negative 5 halves, right? get kind of looking here. All right, so now we just do the same process, don't we? Right, so we bring the 1 down. 1 times negative 5 halves is, if I add those up, I get negative 10 halves. So what is that? Yeah, good. Okay. Negative 5 times negative 5 halves is positive.
Is 52 halves, which is 26.
Okay, negative 2 halves, which is negative 1.
I don't know how that
Remember, we're adding instead of subtracting. It's opposite of long division. Negative 1 times negative 5 halves is positive 5 halves.
Well, that's -6.
Negative 6. Negative 12 halves, which is negative 6. And then finally, negative 6 times negative 5 halves is going to be positive 15. Good. And if I add those up, I get something kind of ugly, right? So maybe we want to think of that as being 30 halves. So we can add those up. Negative 9 halves. Okay? So then if we write out our answer, think what that's going to look like. So this is the constant, this is the coefficient of x, that's the coefficient of x squared, and that's the coefficient of x cubed, right? So our answer is going to look like x cubed minus 5x squared minus x minus 6. But then what do we get here? So we've got our negative 9 halves divided by what? Remember, we divided everything by 2,
Yeah,
didn't we?
so X plus 5 halves.
So on the bottom, we've got our x plus 5 halves. We could have taken a little shortcut here, right? If I flip and multiply, or if I multiply top and bottom by what to get rid of the 2 on the bottom? 2, right? Wouldn't that final term just have been a plus negative 9? If I distribute a 2 through on the bottom, I'm just going to get a 2x plus 5. So when we got this final answer here, what could we have done first? Yeah, we could have just recognized that we're just going to multiply that whole thing by 2 to put the denominator back in the form 2x plus 5. Right. Those are a little tricky. I mean, those are, I've never given those to an algebra 2 class before.
So then it would pretty much just be like the old equation.
Yeah.
Like this is only like a certain one though because they're both 2.
Okay, the reason this one was trickier was because of that 2 on the bottom. Right, so you remember the steps are if you got something other than 1 as a coefficient of x in the linear factor on the bottom, you're going to divide top and bottom by whatever that is, right? Do the whole process, and then whatever's in the remainder box, we're just going to reverse that and multiply back through by that.
So you just always do that.
Yep, every time. Okay. And of course, remember, you don't have to use, you can always use long division instead, right? I mean, I think this is easier, I mean, quite a bit easier. That's a lot of steps to do using long division, right? It's a little trickier when you get a coefficient out in front of the x, but you get the idea, right? The rules, it's not that bad. Okay, so for today, what I want to do, we want nothing new, essentially. We're not learning any new math, but I just want you to relate this to another concept. So what this does is it takes that whole synthetic division process that we've been working with, and you get to reuse that for another concept. That process also informs us about what's this function. It gives us some other information about what this function is doing, right? So let's take an example like this. What if we divide some function p of x, some polynomial p of x, we divide that by x minus k, think what the answer is going to look like, right? We're going to get some quotient part that's going to be like the polynomial part of our answer, right? Okay, so there's the polynomial part. Plus we end up getting some remainder divided by the original denominator, right? So we get this quotient part that's a polynomial plus some remainder divided by the denominator. That, in general, looks like this, doesn't it? Right, when we divide a polynomial by a linear factor like this, we're gonna get the regular polynomial part plus the remainder, what remains over the original denominator, okay? Well, what if we were just to multiply each side through by x minus k? That's no big deal, so we just wanna rewrite this algebraically. So if I were to multiply each side by x minus k, I'm gonna get some cancellation here on the left side, the x minus k's cancel, and I just end up with a p of x, I get the polynomial by itself. On the right side, if I distribute the x minus k to both terms, I'm going to get x minus k times q of x times that polynomial part of our answer, plus if I distribute to this second term, the x minus k's cancel. Would you agree I just get something like that? Okay. Okay, that's pretty significant, right? So we know that, well, let's look at a couple examples. Let's look at a numerical example first. So let's look at something like this. What if we're dividing 25 by 4? Just numbers, right? Go back to good old numbers. I know that a long time ago. We didn't have variables, right? So 25 divided by 4, you guys can do that easily. 4 goes into 25 6 times evenly with one remainder, right? So we would say then that the quotient of 25 and 4, a lot of times you'll talk about this in math, you'll talk about the quotient part and the remainder part. The quotient is 6 and the remainder is 1, right? Okay, so what's that tell us then? If I multiply each side through by 4, we know 25 equals 4 times 6 plus remainder of 1, right? If I were to distribute the 4 through the right side, the 4's would cancel in that second term and I get something like that, right? Okay. Same thing we saw here in general. Okay. Now let's look at an example that uses polynomials.
Can you go back to the equation,
Back to that one?
Yes, I can.
Yeah, sure. So same thing here, right? We ended up with instead of this being what was it, a 25 on the other page?
Yeah.
Instead of that being a 25 and that being a 6 and a 4 and a 1, well, now we've got some polynomial function equals x minus k times the quotient function plus the remainder, okay? What if we do that with a specific example? So we'll take the polynomial 3x squared minus 4x plus 7, okay? Well, we could go through this one. I mean, I'm not going to. If we use synthetic division, what we're going to end up finding is that we're going to get a 3 and a negative 1 will be the numbers underneath the bracket, and then in the remainder box, we're going to get a 6 if we go through that process. Okay, no big deal. That takes a second to do, but we don't want to take the time. So if we multiply each side through by x minus 1, I'm just going to end up with the x minus 1 times the 3x minus 1, right, plus the remainder, right? So in other words, 3x squared minus 4x plus 7 is equal to x minus 1 times 3x minus 1, almost. I've got to add this 6 at the end, though, for my remainder, okay? Now, we can take big advantage of that. What if we were to take this exact example here and we were to ask the question, well, what if we let x equal 1? Right, what if we let x equal 1? If x is equal to 1, if we make that substitution, what's going to happen to that factor right there? It goes to 0, okay? So we end up with, if we make all that substitution all the way through, we're going to get 3 times 1 squared minus 4 times 1 plus 7, right, which works out to be 3 minus 4 plus 7. Well, what do you know? What is that? It's going to give us 6, isn't it? 3 minus 4 is negative 1 plus 7 gives us 6. Okay. On this other side, what do we end up getting? 1 minus 1 is 0 times, who cares? 0 times anything is 0, right? Plus 6. Well, yeah, I get 6 equals 6. It has to work. Big deal, right? What did we show there? We showed something important, though. What we showed was that 6 was already there. The 6 was already, at the very beginning, that number 6 showed up as the value of the remainder. Doesn't it have to work that way, though, right? If we're going to evaluate this function at the zero of this linear factor, right, that's always going to cancel, this product is always going to cancel to zero, right? And so we're always going to be left with only the remainder on the right side of the equation. That gave us a huge trick there, right? All we have to do, if we want to know what the value of p of x is at the zero of this linear factor, it's always going to be, well, whatever we get in the remainder box using synthetic division, right? So that tells us that synthetic division not only acts as synthetic division, it also acts as synthetic substitution, right? Let's look at an example of what I mean. What about something like this? What if we take something like that? Let's say we've got this function f of x up here, and we want to evaluate this when x equals -1, right? Well, we could, I mean, and you might be asking yourselves, well, what's the big deal? We just plug -1 in, right? Not a huge deal. But we could, what if the numbers were worse than this? What if the coefficients were pretty big and the value we were plugging in was a pretty big number? Then plugging that number in and doing that huge calculation, unless you have something like Desmos, and that's not a big deal. But if you're trying to do this by hand, without the benefit of any technology, you got to start to, you're going to be expanding out some pretty big terms here, right? Like if x wasn't -1, if it was like 11 or 13 or something, well, 13 to the 5th is a big number, right? You're starting to get some big numbers you've got to compute and then add up the string of really big numbers, right? So yeah, you can do that, but we can also take advantage of the fact that if I plug in, if I plug 1 into this function, what I'm going to get back at the end is whatever I got in the remainder box, right, when I divided it out synthetically, okay? So let's do this one together then. We could just go through the synthetic process. Instead of having to, you know, I agree, in this case it's pretty darn easy to just put -1 in for x. But keep in mind that it's not always that easy, right? So if we just make our little synthetic bracket, what's the zero of the denominator? Well, it's -1, right? So the -1 is going out front, right? What are the coefficients inside? -1, -1, no, 0. How come? There's no x cubed, so 0, 0, -5, and -7. Okay? So now we'll just go through the process. And the process is really quick, isn't it? I bring down the -1. -1 times 1 is plus -1
0,
times -1.
0, 0, 0, 0, 0, -2.
So what's the answer?
-2.
-2. -2 is the value of the function at -1, right? That's the remainder. This is the very same problem. Now, before we knew about this, you could have done this same process if I had given you the problem, simplify -x squared minus x to the 4th minus 5x minus 7 divided by x plus 1, right? If I had gone through that whole synthetic process, you would have found that that's equal to, what is that? There's my constant, x squared, x cubed. That's an x to the 4th, and that's my constant. So that whole thing would have just been equal to -x to the 4th minus 5 plus -2 over x plus 1, right? We don't care about all the other stuff. Here all we want to know is what's in the remainder box. It's a -2. So that's the value of the function, right? See what I'm saying? Works that way every time. So we could go through a more general proof where we didn't specify, like we looked at the example where we picked something, you know, we looked at a specific example and we picked, well, let's pick let's pick the value x equals 1 because that's the 0 of this factor, right? Well, let's not do that. Let's just make it totally general, right? If we know that this is true, then we know that if we know that dividing p of x by x minus k is always going to give us this quotient that we get from synthetic division plus the remainder, right? Well, what if we evaluate this at x equals k, just in general, right? If we evaluate this at x equals k, the very same stuff is going to happen. That's going to go to 0, and so we're going to get p of k on the left side, whatever that is equal to 0 times q of k, who cares? 0 times anything is 0, plus r. So p of k is just always equal to r, okay? That make sense? Okay. So for now, the kinds of problems you're going to do are pretty simple. They're just problems like that. Okay, we just did that one. And we got the answer, -2 is the remainder. Okay, I got another question for you, though, that kind of leads us into a discussion for, in a little bit, right, for a few days. What does this tell you about the factors of f of x? Does it tell you anything significant? Is x minus -1, x plus 1, is that a factor of this polynomial? It has a remainder, right? So let me go back to our earliest example we did, a really simple one with numbers. Is 4 a factor of 25? How come? Because there's a remainder, right? The remainder is not 0. If the remainder were 0, then it would have been a factor, right? Another way of saying that, if 4 had gone into 25 evenly, then it would have been a factor, right? Because there wouldn't have been a remainder. Okay, well, that same logic is kind of cool. You can do this in math. That same logic that we applied to those numbers, we can apply to polynomials now. Right? So I asked the question again. Is x plus 1 a factor of this big polynomial, f of x?
No.
It's not. How do you know? Because there's a remainder. Yeah, because there's a remainder. Right? No. I mean, that's not really. I mean, it's, yes and no. I mean, we know how to do it right now. If the polynomial is a quadratic polynomial, right? If it's a second degree polynomial, we did a ton of that stuff in Unit 2. So yeah, we know how to find the factors then, we factor them, right? Okay, what if it's a cubic polynomial or a quartic polynomial? Well, no, that's what we're going to talk about next. Right? That's kind of the next topic we're leading into, is how do we find those factors. But it's important to know that you can check synthetically. I mean, you can check whether or not x plus 1 is a factor by simply going through that synthetic substitution process, right? If you get a remainder, then it's not a factor. Think what it means to be a factor. Like if we had something like, for example, what if we had something like x plus 1 times x minus 2 is my polynomial, right? So that's equal to, if I multiply that out, what? X squared minus x minus 2, right? If I graph this thing, where are the zeros going to be? -1 and 2, right? Doesn't that make sense? If I start with the polynomial f of x equals x squared minus x minus 2, and we want to know where the zeros are, well then that means if we're looking for the zeros, we just set the whole thing equal to 0, right? We're trying to figure out where is the function, where are the y values equal to 0, right? That's really all we just asked. Where does y equal 0? Now you got to really just focus hard here on this. Some things are going to come together for you. So let's think about that in terms of a graph. Where is y equal to 0 in the xy plane? The x-axis. And I know you know that, but I just want to make that extra clear when you really focus on that fact. So there is the line we're interested in, right? Where does the function cross the x-axis? Well, if we shifted gears back in Unit 2, how did we solve this equation? That's a pretty easy equation. What did we do? factored it, right? We factored it, didn't we? We found magic numbers that multiplied to -2 and added to -1, and we factored it. We factored it into x minus 2 times x plus 1 equals 0, and we got solutions. One solution was x equals
2.
2. Good. So I'm correct, 2. So there's one of them right there, right? The other one we found was at x equals -1, right? That was right there. And we had some parabola that opened up, and so if we were to graph this parabola, it would have just looked like something like that, right? You get the idea? Okay, so it works out that in this case, because the function was equal to 0 at those places, those were the factors of the function, right? We took it in the order in Unit 2. We started off knowing what the function was, and we set it equal to 0 and solve, right? But now, the way we're currently looking at this, we might take a little different approach. We might just say, is 2 a factor of f of x equals x squared minus x minus 2? I mean, it's pretty easy to check in this case, right, because we can factor it so easily, but what if it worked? What if this were a big gnarly polynomial, like a 5th or 6th degree polynomial, and it's not so easy to factor? We could have checked it pretty easily using synthetic substitution, couldn't we? Right, we could have just run this through 1, -1, -2 is 2, so there's the number that goes out front. Bring down the 1, what do we get? 1, 2, 0. So yes, it is. Right? What if it wasn't? If it wasn't, like what if we had checked a value instead of 2? What if we had checked a value like 3? Is 3 a factor? If I plugged 3 in here, I would not have gotten 0, would I? How come? Because out at 3, the value of the function is not 0, is it? Right? So if that's not an x-intercept, then x minus 3 can't be a factor. Okay? That's a lot of stuff I just threw at you there. None of it's new, right? We didn't do anything new. None of the processes were new. But you kind of see the value of that, right? Once again, just to summarize, that's the big thing right there, right? The remainder theorem just tells us that if a polynomial is divided by x minus k, then the remainder of the polynomial is f of k. So if f of k is 0, then x minus k is a factor. Right? That's the way we can always check. Okay? So if q of x is a factor of p of x, I don't really want to use q of x if it was what I wanted. If x minus k is a factor of p of x, then the remainder must be 0. Okay? All right. I'm going to be done. Yeah. We'll come back to that again. When we start talking about factoring polynomials, we'll come back to that. How much time we got? 2 minutes. 2 minutes? All right.
1 minute.
1 minute now.
60 seconds.